Okay, so in the previous lecture, we were talking about talking about the identification spaces, right? So this is the last lecture on identification spaces. Identification spaces, and okay, so let's continue our discussion. So a quick recall, if I give, so let me just recall the geometric overview of how these identification spaces were working. Okay, the algebraic overview is sort of in details in the last two lectures, or at least the algebraic connection between the things which we want to do geometrically using the concept of quotients is described a bit in details in the last two lectures. But let me just talk about a geometric overview, and then we will be continuing our discussion. So what we typically wanted to do throughout is to start with some sec, okay, to start with some topological space, and identify some region of it, as a single point, and using this process construct a new space with a defined topology. Okay, so what we were trying to do, so we started with a space. Suppose this is a space, let's say X. This is a space X. Now what we try to do is that we actually want to divide X into certain disjoint subsets. Okay, so suppose I cut it like this. For example, I cut it like this. Okay, and say like this. Now what are we trying to do is that we are trying to take each of these subsets and identify these to a single point. Okay, identify these to a single point. So for example, and I continue this process, so I then map this part to a single point, I map this part to a single point, and I map this part to a single point. The last partition is also something I map to a single point, and I construct a space out of these points, and this is what I call X mod tilde, where tilde is the relation inducing the partition, or the identification relation, you might also say, or the identification relation. Okay, so let me just give a very easy example to just recall, just warm up for this lecture. That is, suppose let's say X is just my closed interval, let's say 0 1. So X is just my closed interval 0 1, and what I try to do is that I define a relation on 0 1. Now X is a well defined topological space using the subspace topology, right? There is nothing too complicated to talk about. Now what I do is that I define a relation on X where I just relate 0 and 1 and 1 and 0, and I generate out this relation. Okay, this is a sort of a notation for generating relation. Basically what I am trying to do is that, let me not get a bit rigorous at this point. What I am trying to do is that I want to connect the boundary of this interval, connect uh, together as a string the endpoints. Okay, so what I'm trying to do is that I am just imagining this to be a string and I want to tie up these 2 points. So I want to tie up these 2 points, and intuitive enough I'll get something like a circle where the tied point will represent both the point 0, as well as the point 1, right? And the other parts of this circle are still simply the closed interval. Now in this case it becomes the open interval, so it's just the open interval 0 1. The rest part of the string are just the open interval 0 1, so they are as they were before I tied up the string. So this part, if I talk about, this part is still the same as this part, but only what I am doing is that I am just tying the endpoints of the string together, and this is what I call as identification. So here what I am trying to do is that I am trying to identify 0 and 1, that is I want to represent 0 and 1 in this case as a single point, and representing them as a single point I will eventually get a new space which I will be calling the quotient space after, or the identification space, that will be a better term to use. An identification space which we have which is induced by x on identifying 0 and 1. Now this was the basic geometric overview what we did in the last lecture, last 2 lectures. Go and please have a look at the last 2 lectures, because there we had certain important theorems and corollaries which we will be eventually using in the last lecture, that is this lecture itself. Okay, so as said, in this lecture we will be starting with the construction of a cone. Okay, so before giving the rigorous identification of a cone, let us first go via the geometric point of view, and that's exactly the essence to study such things, because it's always what you visualize can be written down on a paper. Okay, unless you visualize things, it's almost impossible to have a have a documentary on that topic, right? You can't document it out unless you have a visualization of what you want to write, whatever. So suppose x is any topological space. Suppose x is a topological space. So x is a topological space, so I am just giving an arbitrary shape to x, let's say. So suppose this is x. Okay, now what I am doing is that let me go step by step. So suppose x is a topological space, and suppose this is my x for now. Consider, so we consider I to be the closed interval 0 1, that's a conventional setup. Consider the product space x cross I. So what are we basically doing under x cross I? So each coordinate, so if I choose a coordinate, so a point, let's say small x from capital X, then with respect to this small x I will get a point of the form x t, where t is in I, that is t is in between 0 and 1, including both 0 and 1. So typically, so if I give a diagrammatic representation of what is actually happening, so suppose this is my x, and I choose a point here x. Okay, and suppose I have this to be in a horizontal orientation. You can think of it as being in a one-dimensional plane as well. So what I am doing is that I am adding an extra dimension to x, to this topological space x, using this closed interval 0 1. So what I am doing is that with respect to x I am just lifting this point up. Lifting this point up with respect to some parameter t, where t is less than equals to 1, greater than equals to 0. So this point you can think of as the coordinate x comma t, right? And so what are we actually doing? So if I talk about a general basis, I am just considering one more copy of x which is being lifted by the closed interval I, and eventually we will get a surface of this form. So I am just we will be getting another copy of x, so another copy of x, and we have this sort of a setup. I guess now you guys know. So this thickness comes from capital I, and this is one more copy of x. So typically we are actually trying to solidify, trying to bring out a rectangle out from the ground. You might think of it in that way. Okay, so we started with x and we added an extra dimension to x, and we brought up it a bit to get another copy of x on the surface and on the bottom, and the walls are created by this closed interval I. So you can think of it in this way. Now I want to form a cone out of it. So my goal is to find a cone, and this I had mentioned in the first lecture, I guess, that all these geometric constructions which we are going through, that is some sort of a deformation or some sort of identification, some sort of squeezing, all these things are sorts of continuous changes. These are sorts of continuous deformations. Every step we are taking, every process we are making these surfaces go through are all continuous processes, and there are no discontinuous processes. There are no jumbled jumping and discrete processes going on. Clear? Okay. So I want to make it into a cone, and if you slightly recall how the structure of a cone looks like, then you might think of it being, for example, yeah, I can think of it in this way. Suppose I identify this, the whole surface which is at the bottom, the whole surface to a single point. Okay, I identify this whole surface to a single point. So what is the coordinate of any pair of points in the bottom surface? So it's just the coordinates x comma 0. I relate it to the coordinate y comma 0, and I do it for all x y in capital X, and this is my generating relation, right? So what I'm trying to do is basically, so I choose any arbitrary 2 points from this space. So let me just write it like this. Okay, so this is the space I have. So I choose any arbitrary point to choose out from this space. So this is suppose x0, this is suppose y0. I identify them up, and I do it for every point present in the bottom surface. So evidently what happens is that the bottom surface just gets squeezed down. So the above surface is as it is. So from here I can say that x cross I identified by the relation tilde is basically, so the above surface was as it is, so it is just x, and the bottom surface just gets squeezed to a single point, and the other cases appear as they were. So eventually what we get is a cone, right? So yeah, I get a cone in this way, and that's I guess enough, right? Okay, if you carefully observe that we had also we could also squeeze the above surface and we will still get a cone, right? So let me just add it in a way that if the generating relation would be of the form x1 identified with y1 for all xy in capital X, then x cross I mod tilde would also generate a cone where the above surface will now be identified to a single point, and the bottom surface x will be as it is, right? So this surface x will be as it is, and we will have ultimately this sort of a setup, right? Right. So in either ways we can form a cone out of x cross I. We can either squeeze the bottom x or we can squeeze the upper x. Clear? So having this relation, so what should be the partitions? What should be the immediate partitions? So just rigorously we can, without explicitly talking about, without explicitly talking about a relation, if you recall in the previous lecture, actually we have generated the discussion on identification spaces in terms of these three things. One is that we started with the relation and we formed the equivalence classes, which eventually led to formation of partitions. This led to one sort of an identification, and the other identification we talked about was to directly start our concept with partitions, and we will talking about these partitions in such a way that 2 points identified will be in the same subset of the partition. And eventually we will see that the concept of equivalence classes and these partitions will be actually same, or rather equivalent to talk about, because if I start a discussion with partitions, then I can just establish a relation between 2 points which belong to the same subset of the partition. The equivalence class with respect to this equivalence relation will eventually give back the same partition we started our discussion with. The third sort of a definition or generation of the discussion of identification spaces was to start with a surjective map between two topological spaces, and to topologize the, or rather to talk about this map in such a way that a subset of Y, which is the codomain topological space, will be open if and only if and only if its inverse image in X is open, right. This somewhat gave us the largest topology on Y such that this map F is continuous. And if I slightly manipulate this discussion, I will eventually lead this discussion, which we started completely from the notion of a topology, notion of a continuous function, but we will be eventually landing up to the concept of partitions again. And so all typically all the definitions of identification spaces are actually the same, and the equivalent and homeomorphic cases. Okay. So these things I have discussed slightly in the previous lecture, so please go and have a view. Whatever. So I can what I can do is that since I have already structurized that which points are to be identified, so I can directly talk about the partitions when we are talking about the construction of a cone. So rigorously, without explicitly talking about a relation, we can talk about the partitions. So I know that 2 points are to be identified whenever they are of the form x comma 0 and y comma 0, or x comma 1 or y comma 1. So let me just talk about let me just talk about the bottom surface. I think that will do. So what I am trying to do is that, number 1, so what should be the partitions? First thing, it should be all points x comma t, all points x comma t such that x is from capital X and t is less than equals to 1 greater than 0, and I want to squeeze down the bottom surface. So the bottom surface, every point in the bottom surface, all of the points in the bottom surface, they all must be in the same subset of the partition. So the collection of all these points, so one partition will be just the collection of all these points x comma t such that x is in X and t is exactly equal to 0, and the best way to write this is just x cross 0, right. So you have these two subsets of partitions, one which contains singleton sets of all points of the form x comma t, where x comes from X and t is less than equals to 1 and greater than 0, and one subset of the partition will contain all points from x cross 0, right. So this will give us the cone where the bottom surface is squeezed, and to have the top surface to be squeezed, then I just need to change the boundary of the parameter. So just this is a very extremely easy sort of case. So justify, or rather give the partition if the above surface is to be squeezed. Clear? Okay. So yeah, that's good to go. Now this is the identification space in terms of this relation we get, or in terms of this partition we get, is what we call the algebraic cone of X. So it is this cone, this we denoted as Cx, is called the algebraic cone, of X. Okay, is called the algebraic cone of X. Now I need to talk about what is the concept of a geometric cone of x. So let me just briefly introduce what is the geometric cone of x, because there is nothing too complicated to what I am trying to discuss. So what is the geometric cone of x? Okay, so see, the specific structure, the specific geometric structure of a cone, it seems like that we start with a surface and we start with a point, and then the structure we get by connecting the specific point to each point on the surface is basically a cone, right? So typically so we start with a point. For example, we start with a point and we start with an arbitrary surface. I do not need to intertwine them. So I start with an arbitrary surface, and what I do is that I connect each point on this surface with this point. So suppose I do this, then I do this, and you can think of it, sorry, I need to connect the boundaries because I am talking about a cone typically. So I have this, then I have this, and it's sort of like this, right? Okay, so I should have talked about, yeah, right, this is some sort of, you can think of it some sort of as a cone, right? Okay, and the typical case is that in fact I can also actually, because see, this cone is in fact it's can I say that this cone is filled from inside? That's one question I should obviously talk about. Should I consider that this cone is filled from inside? Because see, I am starting with the surface x and I am lifting the whole surface by some width, right? So the inside is typically filled, right? So I just just attach this cone, this point to each of the elements within itself, let's say, this sort of construction, I guess. So if I just talk about the geometric definition of how we can define a geometric cone, so how do we start with? Okay, so for that what we need to think of is that I need a bounded surface, and it will be extremely helpful if this is closed, that it contains its boundaries. So in fact it's the best to talk about a compact subspace, and a compact subspace of an n dimensional Euclidean space is worth talking about. So let X be a compact subspace of Rn, and inside let's say include Rn in Rn plus 1. So what are we doing? We are just attaching an extra dimension to Rn to make it as a subspace of Rn plus 1 as the set of points, So what we do is that we just consider Rn to be a subspace of Rn plus 1 with just the set of points x1, x2 till xn, and the n plus 1th dimension, the coordinate which measures the n plus 1th dimension, is just left to be 0. Okay. Now what we do is that, now you can easily guess this from the figure I have drawn, that if I consider, suppose I consider this to be R2, for example, I consider this to be R2, and I am adding this extra dimension to R2, then this point, this specific point which I am using to join the surface X, that point is in the extra dimension which I have constructed. So let V belong to Rn plus 1 such that, so I want V to be in the extra dimension, so I can just consider V to be the point which has zeros in all the dimensions and only 1 in the last dimension. Clear? And now what we basically try to do is that we want to connect V to each point of the surface X, and that's all what we want to do to find the geometric cone, right? So you can think of it in this way. So define the geometric cone of x, or also I guess it's also called on x, to be the collection. So I want this surface, right? I want this surface. So this surface is typically a collection of these lines, right? This surface is basically a collection of all these lines which are connecting the specific point V to the surface x. So define the geometric cone of x to be the collection of points En plus 1, or rather let me talk it in this way, to be the collection um, of all straight lines, straight line segments to be precise, that join V and each point of x, that join V to some point of x will be a better grammatical statement, that join V to some point of x. Clear? Right. Now this statement is though quite geometric in nature, you can visualize what I am talking about, but since we are talking about a topological space, it is better to give sort of a point structure to it. So we can also talk about, that is so Gx, which I will be referring to as the geometric cone of x. So Gx is the collection of all points of Rn plus 1, which can be written as, so I actually want to represent each line, so it's better to consider points which can be written as the equation of lines, so which can be written as Tv plus 1 minus t times x, where x is in capital X, V is the point we started with, and 0 less than equals to t less than equals to 1. You can easily observe that this is just the parameterization of a line joining two specific points, right? So each point in Gx can be considered to be of this form, provided a V and provided a point from capital X. And so the geometric sort of notion is already given, so there is no point of talking about it in a more geometric way. Rather, what I actually want to discuss is that claim. Now this claim is quite intuitive, because we have talked about two specific topological structures, both of which are by some sort induced by the same topological space. One is the algebraic cone on x, which I have represented as Cx, and one is the geometric cone on x, which I have represented as Gx. But intuitive enough and geometric enough, in fact, both of these are topologically the same. So the claim is quite intuitive and straightforward, that is Gx is homeomorphic to Cx. That is exactly what I claim. So, and the proof of the claim is quite easy to observe. I just need to construct a surjective continuous map. And why do I need to do so? In the previous lecture, there was a very fine way to talk about identification maps. What all we need is an identification map, right? So an identification map is the map which corresponds, which acts as the correspondence between the topological space we start with and the quotient space we finally induce. An identification map, if you so justify that an identification map is some sort of a homomorphism by any cost. Okay. So 1 second. Okay, so I want to claim that the geometric cone is homeomorphic to the algebraic cone. So what I do is that I construct a map f from x cross I to Gx by, so what I do is that I map each point xt to the point which I should be mapping it to, Tv plus 1 minus t times x. Clear? Now the thing which is quite easy to observe out is that now f is continuous, which is quite easy to observe, if is continuous onto, and f is 1 1 on, yeah, so so f is continuous onto, and what we can observe is that, see, so it's onto whenever I talk about, yeah, I can think of it in this way that, see, f is surjective, this is quite obvious, and continuous, this is clearly quite obvious. So, if it is surjective and continuous. Now, suppose I want to check whether f is injective or not. See, if you recall the previous lecture, the last discussion we did, in that case we observed that if I want to identify 2 points or a certain region on a topological space, then firstly I partition it out, and the subset of the partition which contains the points to be identified, the whole space except that very subset, on that space, if the map is injective, okay, and furthermore the map identifies the whole subset, the whole specific subset to a single point. Moreover, the map is such that it is the largest, it induces the largest topology on the range set, such that that specific map is continuous, and it's surjective. In that case, we can talk about it being directly an identification map. And in the last lecture, we had also talked about that if I start with a surjective map, surjective and continuous map between two topological spaces, where the domain topological space is compact and the codomain topological space is Hausdorff, then f is evidently an identification map, and that thing will clearly work in this case. Why it will work? Because you can easily observe that f is surjective and continuous, that is quite trivial. Now, if I consider f of x1 t1 to be is equals to f of x2 t2, then I will eventually get that x is equals to x1 is equals to x2, t1 is equals to t2, but this might happen, or t1 is equals to t2 is equals to 1. That is, you can easily observe that the space which I have, where I consider these partitions x1, right, the elements which have the extra dimension coordinates to be just 1, all those spaces are being identified to a single point. This map is acting, this map is basically taking all the elements which have the ordinate 1 to a single point, and on the rest of the surface the map is 1 1, the map is clearly injective. Hence, this map will give an identification map, because therefore f is an identification map, because, so it is clearly observed that x cross I is compact, because we started with x being compact and I is also compact. So, x cross I is compact, and the geometric cone, this is a subset of the Euclidean space Rn plus 1, and Rn plus 1 is Hausdorff. So, Gx is also Hausdorff. So, using the previous the corollary which we had discussed in the previous lecture, that if I have a surjective continuous map between a compact and a Hausdorff space, with the compact one being the domain and the Hausdorff one being the codomain, then we can talk about it being an identification map. I guess this part is clear. So, we end this lecture with two specific examples, where I will be simply discussing the geometric point of view, and I will try to avoid the algebraic point of view. So, let me just come up with these. So, first thing which I want to discuss is the Klein bottle. So, is the sort of a Klein bottle. So how do we identify a klein bottle? How do we construct a klein bottle? So what I start with is the simplest thing to start with all examples. So I start with a square, and what I do is that I identify each of these vertices in a reverse direction. Like in the previous lectures we had seen that we were identifying either of them to be in the same direction, but in this case what I actually want to do is that I want to identify the vertical edges. I want to identify the vertical edges to be in the same direction, and I want the horizontal edges to be in the opposite orientation. Clear? This is what I want to do, and I want to see that from what sort of an orientation would I eventually get. So what does these arrows mean? So I want to, okay, I missed it here. I want to make this in the reverse orientation. I want to make up this, yeah, correct. So what I am trying to do is that I am trying to identify the vertical edges in the same direction, and I want to identify the horizontal edges in the reverse orientation. So now the first thing which I can do is that I can directly identify the vertical edges. So I will just roll it up. I have done this in the previous lecture, so I am not doing the middle step. So I can just roll it up, and I'll get this sort of a structure, right? I'll get this sort of a structure, and then I'll roll it up once more, and I'll get a sort of this thing where this there is this middle line which will represent this edge, and then we have the orientations as they are. So let me just change this color a bit. I want a lighter shade. So yeah, this is a bit of problem. Yeah, I guess this will be doing. So 1 second guys, 1 second. Yeah, okay. So I have this sort of an orientation. Yeah, so I have this here and this here, right? This here. Yeah, correct. Okay. So now I want to identify these two edges, the upper and the bottom surfaces. So first what I do is that I just place it horizontally. So I first place it horizontally. So I have this edge, I mean this surface and this surface, and I place it horizontally. Okay. Yeah, so I place it horizontally, and yeah, this is the surface of some sort of how it should look like, and then I give the orientation. So I have this orientation here in this way, and I have this orientation I guess here in this way. So they are in the opposite directions, right? Sometimes drawing this these cases are also quite difficult to observe. Okay, correct. But you can easily observe that in any way I can't actually adjoin these two surfaces, right, because their orientations are always different to each other. The only possible way in which I can actually adjoin these two circular surfaces is if in any way I can bring both the directions of the surfaces in the same case, in the same way. Okay. So what I try to do is that I first place it vertically once more to have a visualization. So I have this surface as it is. So I have this case, and I had this thing, but what I am doing is that when I am actually putting it in a vertical case, you can easily observe that both these surfaces are actually oriented or directed in the same direction, right? Okay. But still there is a slight problem that a self intersection is actually happening if I want to adjoin these two surfaces, because see, if so, let me just draw this part a bit big. So what I am having is that I am having this sort of a structure. So I am having this sort of a structure. Yeah. So yeah, so I am having this sort of a structure. This is too problematic to draw sometimes. Okay, yeah, okay, I guess this will do. This is still presentable, I guess, right? Okay, but the problem is that I want to adjoin these two surfaces, right? I typically want to adjoin these two surfaces, but to adjoin them I cannot have this adjoining from above, because in that case I will still get a two different directional orientations. I do not want that. So the only possibility, if in some way I can adjoin these two surfaces, is to go through the surface itself, and get fixed up here, and so this is basically called a self intersecting surface, or a self intersecting manifold, which is a more technical term, or self intersecting manifold, and it somewhat takes the shape which is some sort of looking like this. So I have the surface and I have this line which goes straight away here, and then this is somewhat coming like this, but it goes through the inside of the tube itself and it connects back to the same surface, and I have an orientation here, and this is what we call a Klein bottle. And how are we typically identifying this up? So I am simply starting with I2, that is basically I cross I represents the closed interval 0 1. So I am just starting with the unit square, and what are the points I am typically identifying in this case? So what are the points I am typically identifying in this case? So I am identifying the vertical edges, which can simply be identified as the points 0 y identified with the points 1 y. So this is one identification, and what is the other identification? So I am identifying the horizontal edges in reverse direction. So I am just identifying x comma 0 with 1 minus x comma 1, right, and I am doing this for all x y in capital X, and this identification space will actually give me the Klein bottle, right. In fact, if you study algebraic topology a bit rigorously, you will eventually see that a Klein bottle eventually gives rise to two Mobius strips. So you can actually think of two Mobius strips with a certain operation defined on these two Mobius strips to adjoin them together will eventually give a Klein bottle. Whatever, that is not a topic of this discussion, but what I wanted to discuss is this. And the next example is the identification space of balls and circles. Okay, so this is basically the last identification space I would like to talk about. So consider Bn, okay, that is the n dimensional unit ball. Bn refers to the n dimensional unit ball. So Bn is defined as the collection of points x1, x2 till xn, which forms an real n tuple such that the norm of this as a vector is less than or equals to 1. So what is the standard norm defined on Euclidean spaces? So this is this norm, this should be less than or equals to 1. So this is the n dimensional ball, it includes this boundary, so it is basically the closed ball, and see, I can actually talk about in this way. So this is an example. So what is B2, for example? What is B2? So it's just the unit disk in R2. It's just the unit disk in R2. So what does it look like? So I have a unit circle. Yeah. So I have a unit circle. 1 second. I guess this will do. Okay, so I have a unit circle and I consider all its insides. So this will give me the unit disk. Now if I just consider the boundary of this circle, then I will get, see, this is a two-dimensional plane, right? This is a two-dimensional figure. This is indeed a two-dimensional figure. but we had previously observed that the closed interval 0 1 is homeomorphic to the circle, to the unit circle. So if I just talk about the boundary of B2, so if I just talk about the boundary of B2, there is the symbol which we use for the boundary of B2, I will get a circle S, but if you carefully observe that the dimension of this circle is one less than the dimension of B2, so it is just S1, right, a one dimensional circle you might think of. Though a circle, to draw a circle we need the two dimensional surface R2, because I can't draw a circle on a one dimensional plane. So to draw a circle I need R2, but since the circle is homeomorphic to 0 1, and you can easily observe that a circle technically has no width, it typically has just a length. You can, the structure of a circle is simply a string, it's sort of a string. So it's indeed a one dimensional structure embedded in a two dimensional surface. Whatever, on a similar note, once we have defined what Bn is, that is what is an n dimensional ball, I can define what an n dimensional circle is, in fact what is an n minus 1 directional surface is. So given Bn, define Sn minus 1, because we have already seen the dimension comes down by 1, to be the boundary of Bn, and therefore I can define Sn minus 1 typically to be the collection of points x1 till xn, which is in Rn, such that summation xi squared is equals to 1, is equals to 1 to n. Clear? Clear? Okay. Okay. So now our goal is to consider, our goal is to identify the boundary of Bn. So what I want to do is that I want to identify the boundary of Bn. In other words, provided Bn, I want to squeeze Sn minus 1 to a single point. That is, I want to identify, or I want to squeeze the boundary of Bn to a single point. So to have a rigorous notion of what I am trying to do, let us first go via the geometric visualization of what I am trying to do. So you can firstly you can observe that to do this, the partitions, what I need is that the partitions needed are, so I just need to identify the boundary, right. So the set Sn minus 1, right. So one partition will one subset of the partition will be the boundary of Bn, which is Sn minus 1, and all the other points except Sn minus 1. So the set containing each distinct points of Bn minus Sn minus 1, right. This part is pretty obvious to understand. Now let us go via a visualization example. So what I do is that I start with a two dimensional ball. Okay, I start with B2. So there's things inside, and what I want to do is that I want to squeeze down its boundary, right. So what I want to do is, typically I want to identify this point with this point, I want to identify this point with this point, I want to identify this point with this point, and what is the best way to do so? So what I do is that I fold the disc along the y axis. So a better way to understand is that you can think of this as being a bread, a roti, in typical term as being a roti, and I am trying to convert it into a taco, right. So if I fold it along y, so I will get just this line to be, for example, y, and I will just fold it in this way. So let me do it in this way. So I will be having a structure like this, right. I guess you are getting what I am trying to observe, right. So I will get a structure in this way, right, and this is basically the boundary of b2 in this case, right, and then I'll adjoin these two and I'll get a half circle, right. I'll get some sort of a half circle. I'll get some sort of a half circle, sorry, not a half circle, a half disc. Extremely sorry for using the term a half circle, because circles and discs are not at all the same thing. Circles are just the boundaries, discs are the complete surface. So what I get is a half disc. Now since we are all talking about continuous deformations, and whenever we talk about algebraic topological cases, we can do anything with a surface until and unless it's continuous. Till it's continuous, so everything is elastic, everything can be stretchable, everything can be twisted, turned, till it's continuous. What I can do is, in this case, I can consider this half disc to be stretchable, to be elastic, and I inflate it out. I inflate it, and if I inflate it, I'll get some sort of a ball like structure, some sort of a ball like structure, an inflated ball. So it's basically an inflated ball, and you can easily observe that. So this can be identified as a sphere, and a sphere technically is S2. So it's the two-dimensional version of a circle. It's the boundary of B3. It's the boundary of a solid disk. It's the boundary of a solid sphere, right? It's the two-dimensional variance of a circle. So it's just a sphere. Whenever I talk about spheres, I am not talking about a solid sphere. Sphere just resembles the boundary S2. It resembles the boundary. It resembles the boundary of B3. B3 represents the unit ball in 3 dimensions. Okay. And therefore, what I get is, typically the thing to observe here is that I start. So whatever we did is specifically not not particular about the dimension I am working with, because these continuous deformations can be extended to any dimensions. So thus, on a general note, if I start with Bn and I identify its boundary, then this will be homeomorphic to nothing but Sn. Clear? So identifying the boundary of an n dimensional ball will give you an n dimensional boundary of an n plus 1 dimensional ball. Okay. So this is what we typically have, and Bn upon Sn minus 1, this is some sort of saying that. So this is just a thing to observe, that if I write x by a at some point, then this means that a as a subspace of x is being identified over x. Clear? Okay. So I am not proving this up, but I am just giving a hint. So this will be the exact thing which we just used while proving that the algebraic cone is homeomorphic to the geometric cone. If you just take a function f from Bn to Sn, such that f is onto and 1 1 and continuous on every point except Sn minus 1, and it identifies Sn minus 1 to a single point, then I can talk about f being an identification map, because Bn is compact and Sn is Hausdorff, right. So the points you might, so see, you can do this on your own at any cost. So I am just writing out the points which you need to be talking about, and you can prove it in a very simple way. So first thing to justify is that Bn is compact and Sn is Hausdorff. This is the first thing, and just keep in mind we are working in Euclidean spaces. Number 2, f is 1 1 onto I should better be saying f is 1 1 onto and continuous on Bn except its boundary, and f maps Sn minus 1 to a single point. to a single point. So 1 and 2 will give f, therefore f is a identification map, is an identification map. So that thing, so these two things will justify why do we have this homeomorphism, why do we have this identification. And so the concept lies in how to construct f, how to construct f. So the only thing to check here is that we know that Rn is homeomorphic to the n dimensional ball except its boundary, right. So the n dimensional open ball is homeomorphic to Rn. You can just relate this to the fact that the open interval 0 1 is homeomorphic to R, is topologically equivalent to R. In a similar case, the n dimensional open ball is homeomorphic to the n dimensional Euclidean space. And so this is the first thing to observe. Moreover, if you recall that in case of an n dimensional sphere, I can just remove a point and we are still homeomorphic to Sn. So Sn minus a point P is so sorry, what I am trying to do is basically number 2 is that if I talk about Sn and I subtract a point out from Sn, so yeah, this will be homeomorphic to En, correct, this will be homeomorphic to En, right. So suppose this homeomorphism happens via H1, this homeomorphism happens via H2, I can somehow define Fx to be the map H1 of H2x whenever x is in Bn minus Sn minus 1, and I can just map it to be P for x is equals to Sn minus 1, and this F will give us our identification map. And why it will give us the identification map, that is enough justified, right. Okay, so that's all for this lecture, and I will be trying to come out with some important topics on topology whenever I feel like. So meet you guys in the next lecture, and this is the end of my discussion on identification spaces. Okay, so meet you guys in the next lecture.